Okay, so our new schedule. Tuesdays, I will try to find a room at 13:40, 1 hour. Friday at 12:40, 2 hours. And Saturdays at 14:40, 2 hours every other week. That is for the time being. Now, if some of you start not to show up on Saturdays, we will just shift the Saturday hour to those who are showing up. Well, still that is kind of the best among the worst solutions. Okay, so let's come back. Now, any questions on this one? Any comments?
I just asking for those items to understand first. Would it matter to anyone if we do it Sundays? If yes?
Sunday?
It's okay for us. Just asking.
No, I mean, Sunday is fine, but I mean, well, for me it's fine. Both of them are bad enough, right? But the hours is, again, between 1:30 up to 3:30. So we should start between that time. Sunday, any objection to Sunday hour? No, the most extreme lecture I had was for a summer school at 6:40. And when the professor was asking if we were objecting it, he said that, I know that you are not objecting because you are waiting for somebody else to object. But we had the 6:40 lecture. So if you're...
On the morning.
Yeah. Summer school, on the morning. Well, I had asked for it. So if you have any objections to the Sunday hour, you should speak now. Until the end of the semester. I mean, you can complain in the pink forms. Okay. So, Sunday? Starting from this Sunday. So in 2 days, Sunday is also in a sense better because at least you will have one more day to, well, that is like the lecturer's dream that the students review it today or the day after.
And on Sunday I can do 1:30 if you want. It's not appropriate.
What do you prefer? I mean, for me it's fine. Huh? 1:30.
Did you do a review when you were undergraduate? Daily?
No. Well, what I did was I reviewed it before. I used to read the lecture notes during the summer, the books. And I do advise you to do it, by the way. I mean, when you come here, I mean, in the first year students, I just force them to read the chapter before coming to the class. But I kind of feel stupid to force it to fourth year students, so I'm not going to force you for attendance or reading the chapter before coming, but I strongly advise you to come having already read. I mean, so that you have an idea about what we are talking about. You build the skeleton by just reading through. You just fill the gaps while listening, and you have questions to ask. And we can concentrate on the points that are not so easy to understand. Okay, so let's continue with the time-independent perturbation theory. Now, there were the main conclusions we had derived from our discussions from last week was we the first order correction to the energy was nothing but the expectation value of the perturbation to our system. And we had said that we had an H0, which ideally we know the solution of. Then there is this additional term H prime that we add to our system. It can be just a small perturbation. We will do some examples we will look at some examples of this perturbation. And the first correction to the energy eigenvalues was nothing but the expectation value of this perturbation in the unperturbed energy eigenstates. And the correction to the wave function itself, we had also written it as the sum over all the eigenstates. Let's call this psi n, the nth energy eigenvalue, and the nth energy eigenstate was psi k 0, psi n 0, h prime, psi k 0 divided by E n 0 minus E n k, assuming n is different from k. Now this condition just came from because we had imposed the boundary condition that any correction to our wave function delta psi n, its overlap with the unperturbed state should be 0. And this we had just treated as a boundary state to our equation. Now, this is, of course, valid in non-degenerate perturbation theory. Now, when there's perturbations, these expressions have problems. If you look at the energy correction, the first order energy correction, I mean, even if there is degeneracy, that doesn't seem to be any problem. But you cannot calculate the first order correction using this approach, if there is a degeneracy, because if there is a degeneracy, there is a state k which is different from n, so it contributes to the sum. But for this state, it has the same energy as the nth state, so En0 minus Ek0. This term just becomes 0 for this degenerate state. Now the way out is basically you take this matrix, in the case of degeneracy, let's say there are these states that are degenerate. You construct the H prime matrix in this degenerate subspace. So this is the general Hamiltonian matrix. I mean, if you would take all the eigenstates, this just gives you the Hamiltonian matrices. It will be an infinite by infinite matrix. But if we have some degeneracy, you only concentrate on these degenerate eigenstates, construct this H prime matrix only in that degenerate subspace, let's say, and then diagonalize H prime. So you just find a new basis, a superposition of these degenerate states. Now that superposition of degenerate states also is degenerate with the other one. So it's, I mean, the problem with the degenerate states is that there is no unique choice of your basis. Any linear combination of your degenerate bases, degenerate states have the same energy, so it can be a member of your state, of your complete basis. Now, which one to choose? You just choose the ones that diagonalize H prime. Now, if you make such a choice, then this matrix element that appears in the first correction, then, okay, the denominator becomes 0, but the numerator also is 0. So that if you choose if you choose a basis that diagonalizes H prime in this degenerate subspace, then the numerator is already 0, it doesn't contribute, so there's no problem. So there's no problem in the first expansion. So basically, instead, you just choose some basis states. If some of them are degenerate, then you have this freedom of choice. It's up to you which combination to choose. And then you use this freedom to choose a basis in which the above matrix elements are 0 between two different degenerate states. That's the main truth. So this is the main conclusion about our derivations on time-independent perturbation theory. And the next we will be just applying these to various systems. Now we will start with the hydrogen atom, but before starting the hydrogen atom, let's do an example. Now we had skipped the identical particles, but did you study to some extent at least fermions and bosons? Do you know what fermions are, what bosons are? So you have studied multi-particle state wave functions. Two particles. I mean, that's what I will do. Okay, so let's look at this example from your book. So let's assume that we have two bosons in a potential well. Let's just simplify it in an infinite potential well. And then we add the H prime is equal to, let's say, lambda x1 minus x2. So they also, I mean, initially they are non-interacting. H0 is equal to P1 squared divided by 2m plus P2 squared divided by 2m plus V. And V is V of, let's say, x. X is 0 if x is between minus L over 2 and plus L over 2, and it is infinity otherwise. So this is our system. So basically, here what we are actually doing is we have these two bosons that are free. If they are at a distance, they are not influencing each other. They don't see each other, but they can still collide. They can hit each other. So when they are at the same point, they just hit one another. Now first, let's try to solve the Ampere H0. Now the wave function, it will depend on x1 and x2. x1 and x2. This is x1 or x2. If both of them are between that range, it's 0. Outside is infinity. Now we can write the solutions as psi 1x1, psi 2x2. Do you agree?
This is for fermions.
Okay, for bosons, what should I do? Or is it for fermions? Why did you say that it's for fermions?
Doesn't they influence each other if you multiply them?
I don't know. I mean, you tell me the answer. Well, I know the answer, but... So how do you write the wave functions for fermions or bosons, for identical particles? Okay, let's have a short review. Now, we have this wave function of two particles. I mean, the treatment you can just generalize to any number of particles. Now, what does it mean to be identical? We cannot distinguish. I mean, classically we say, okay, one particle is here, the other particle is here. But I mean, if we just change them, nothing changes. Nothing should change. Well, we measure the probabilities, so the probabilities shouldn't change. So we should have these probabilities. Now, the best way to have this one is, well, the only way for this to be valid is this should be equal to some lambda psi x2 x1. Now, psi x2 x1 should lambda psi x1 x2. That is, psi should be such a function that if you just change the coordinates, it just gets a factor of lambda. But I can just do the same trick over here. I can exchange x1 and x2 in that psi, but that should also bring me another factor of lambda. lambda squared psi x2, x1. So lambda squared should be 1, which tells me that lambda should be equal to plus or minus 1. So if you just, that is psi x2, x1 should be plus or minus psi x1, x2. If you just exchange the two identical particles, your wave function should either stay the same or should acquire a minus sign. Now these two particles are what we call the bosons. Lambda equals plus 1. These are the bosons. Lambda is equal to minus 1. These are what we call the fermions.
I didn't understand why the wave function doesn't get any phase but plus or minus 1.
Well, let's just say lambda. This condition tells me that lambda. Okay, I have this condition. Okay, so any questions on why we have that condition? The system shouldn't change. Nothing observable should change. Well, if that condition... Well, yeah, in a sense. In the second one, if you consider this relation, this combined with the previous relation already tells me that lambda, its absolute value should be 1. It should be a phase. So what is that this relation? This tells me that what I do from the left-hand side to the right-hand side is that I just exchange these two arguments of my wave function. So if I exchange the arguments of my wave function, okay, although here we write 1 and 2, I mean there's no this 1 and 2, it's just the exchange of the arguments, whatever the arguments are. If I exchange the arguments, I should get this lambda. So psi x2, x1, exchange the arguments, I get lambda times psi x1, x2. But here you see I have psi x1 and x2. I can change its arguments also. If I make that exchange, it also becomes lambda times psi x2, x1, or let me write it this way. So psi x2, x1 should be equal to lambda squared times psi x2, x1. So lambda squared has to be 1. And I have two possibilities. Lambda should be plus or minus 1. Well, I mean, if you go to, let's say, 2 dimensions or 1 dimension, there are some other possibilities. I mean, if you are interested in mathematics, I would suggest you to take some algebraic geometry course. Okay, so there, for example, you will see that there is no restriction on lambda. Lambda can be in any phase in 2 dimensions or in 1 dimension. But in 3 dimensions, lambda should be either plus or minus 1. Now, other values of lambda. Look at parastatistics. Now, at some point, there were some phenomena which we couldn't really explain in two-dimensional electron gas systems, like the quantum Hall effect. And people were trying to apply these parastatistics, where lambda can take any phase. It doesn't have to be plus or minus 1. Now, anyway, so we will stick with the conventional case. We have the lambda is equal to plus or minus 1. Now, lambda is plus 1 are the particles that we call the bosons. Lambda is equal to minus 1 are particles that we call fermions. And it turns out that this lambda is equal to plus 1 or minus 1 has a close connection with the spin. So bosons are particles with integer spin. For example, particles that have 0 spin are bosons, like the Higgs boson. We call it a boson because we know that its spin is either 0 or 2 or 3. In any case, it is integer spin, the particle that we observe. Theoretically, it has to be spin 0. It's a boson. The fermions are particles with half integer spin. For example, photon, that is the quantum of light, it has spin 1, so it's a boson. Electron is spin 1/2, so it's a fermion. Proton, it's a spin 1/2 particle, it's a fermion. Hydrogen atom, it's a boson. Its spin is either 0 or 1, so it's a boson. Deuterium atom, deuterium.
How many electrons?
Well, deuterium has 1 proton, 1 neutron, and 1 electron.
Fermions.
It's a fermion. Helium, helium 4. 2 protons, 2 neutrons, 2 electrons.
As long as it is even, it's a boson. As long as it's
Yeah. So helium 4 and helium 3, they have a completely different behavior under very cold temperatures. So that affects their, for example, superfluidity. Helium is a well-known superfluid at very low temperatures. But helium 3 and helium 4, they just behave completely differently because one is a fermion, the other one is a boson. So now let's come back to our problem. We are dealing with bosons. This cannot be the wave function of a boson. It also cannot be a wave function of the fermion, by the way. Because if you exchange x1 and x2, it's neither symmetric nor antisymmetric. If it's for a boson we have to add psi 1 x2, psi 2 x1, 1 over square root of 2. This is the wave function. But let's just forget about their fermionic or bosonic degrees of freedom for the time being. This here we have a differential equation satisfied by this psi x1 and x2. We can just use separation of variables. And separation of variables tells me that h0, I can put the psi 1 x1, psi 2 x2. This should be equal to e psi 1 x1, psi 2 x2. I can look for such a solution. Well, h0 we know what it is. It is, let me write the minus h bar squared over 2m d squared by dx1 squared minus h bar squared divided by 2m d squared by dx2 squared. Let's write the potential x1 and x2 between minus L over 2 to plus L over 2. Anyway, the wave function should be 0 at the boundaries because we have this infinite potential zone. Now, in that range, we don't have any potential. Anyway, these are partial derivatives. Psi 1, psi 2 should be equal to E times psi 1, psi 2. Well, this, if I just take the derivative, psi 1 depends only on x1, psi 2 depends only on x2. So this gives me minus h bar squared over 2m psi 1, the second derivative, times psi 2 minus h bar squared over 2m psi 1 times psi 2, second derivative. This should be equal to e times psi 1, psi 2. Now let's divide by psi 1, psi 2. Well, I'm just following the general trick for separation of variables. If you divide by psi 1 and psi 2, you get minus h bar squared over 2m psi 1 double prime divided by psi 1 plus minus h bar squared divided by 2m psi 2 double prime divided by psi 2. This is equal to E. Now this depends only on x1. This depends only on x2. And this is just a constant. Now I can just keep x2 constant and change x1. This equation should still be satisfied. But if I keep x2 fixed, the second term is constant, E is constant, so the first term, although it depends on x1, it should also be constant. And similarly, if I can keep x1 fixed and change x2, but the first term doesn't change, the right-hand side doesn't change, so the second term should not change, even if I'm changing x2. And that gives me, let's just call this constant E1, this constant E2, and we have minus h bar squared over 2m psi 1 double prime is equal to E1 psi 1 minus h bar squared divided by 2m psi 2 double prime is equal to E2 psi 2, and the total energy of my system is E1 plus E2. Now we already know the solutions. Psi 1. What are the solutions? Well, let's just, okay, let me just make some definitions. E1 is equal to h bar squared k1 squared divided by 2m. E2 is equal to h bar squared k2 squared divided by 2m. I mean, they're both the same equation, so it's enough if we just solve one of them. So what we have, psi 1 double prime is equal to minus k1 squared psi 1. Do you like the exponentials or the cosine or sines? Okay. So psi 1 is equal to a times e to power I k1 times x plus b times e to power I minus I k1 times x. Now, but of course we have the boundary conditions. We know that psi 1 at x is equal to minus L over 2 should be equal to psi 2 at x is equal to plus L over 2, because the wave function should be continuous, and in a region with infinite potential the wave function should be 0. And this is the boundary, x is equal to minus L over 2 and x is equal to plus L over 2. Now these two boundaries, this should be 0. So I obtain a times e to power I k1 L over 2 plus b times e to power minus I k1 L over 2. This is equal to 0. And a times e to power minus I k1 L over 2 plus b times e to power I k1 L over 2. This should be also equal to 0.
Psi 1 is 1.
Now psi 1, true. Now the argument, whatever the argument is. Well, first of all, these two equations are consistent with each other if A is equal to plus or minus B. This is one condition we have. Now, if A is equal to B, then A times 2A times cosine K1 L over 2, this is equal to 0. So this tells me that K1 times L over 2 should be equal to K prime? K n, no, let's not use the K, n pi. N plus 1 over 2 pi. Or K1, the nth possible K1 is equal to 2 over L n plus 1 over 2 pi. N 0, 1, 2, etc. Now the other case, and psi is equal to A times cosine K1 and x. What is A? How do you determine A? It's normalization. I mean, A can be arbitrary, but since we want to use this probability interpretation of the wave function squared, so we just normalize it to 1. Minus L over 2 to plus L over 2 dx psi of x squared. This should be 1. from minus L over 2 to plus L over 2 dx a squared cosine squared k1n of x, which is no, this is L over 2. So the absolute value of A is square root of 2 over L. Well, the phase is arbitrary. These are just the basis states. So we can just choose the phase to be such that A is real. 2 over L. And we have the solution psi, let's call it plus n equals square root of 2 over L cosine kx, n of x. Okay, this is one possible solution. The other solution, if A is equal to minus B, then psi is equal to 2IA, no. Okay, I will just throw away these 2 and i's. Is some constant sine k1 of x. Again, we have the same boundary conditions. So A times sine k1 of L over 2 should be equal to A times sine k1 of at minus L over 2. Well, this is already automatically satisfied. Both of them are the same up to a sine, but in any case, both of them should be 0. And this tells me that k1 L over 2 should be equal to n pi. Again, n is equal to 0, 1, etc. So the k1 can take values 2 over L, 2 pi over L times n. So we have the solutions psi minus n x is equal to the normalization will be the same times sine k. Well, let me change the notation slightly. Let me put a plus over there, a minus 1 over here. So what can you say about these functions? Is there something that attracts your attention? The cosine and the sines? They are symmetric and anti-symmetric. Why? Is it just a coincidence? Why do you think we have only symmetric or anti-symmetric solutions? Well, this is just a single particle. No, I mean, both the bosons and the fermions can be in both of these states. But why did we end up having only symmetric or anti-symmetric solution? Why not some solution without any symmetry? Sure, but I mean, the eigenstates turned out to have definite symmetry properties. So let's define the parity. So parity just takes x to minus x. So Hamiltonian H0 doesn't change under parity. So it commutes with parity. So if you have any function, you can actually write it as the sum of two functions. So under parity, this combination has positive parity and the other one, now let me just write it over here, has the negative parity. Well, since parity commutes with the Hamiltonian, You have probably seen that if there is an operator that commutes with the Hamiltonian, there's a conserved quantity in the system that doesn't change in time, and you can always choose your eigenstates to be the eigenstates of this corresponding conserved operator. In this case, it is the parity. And the eigenstates should be eigenstates of the parity also. If there is degeneracy, we are free to choose as eigenstates of the parity. If there is no degeneracy, then they have to be eigenstates of the parity. So that's the main reason why the eigenstates turned out to be even or odd. We don't have an eigenstate that is either not symmetric with respect to the origin. Okay, so we have the solutions. Let me just, for notation, let me just choose them as n. Both of them as n. And we can just choose the convention, for example. If n is odd, we have the anti-symmetric one. If n is even, we have the symmetric one. But that n, by the way, is different from the n over here, just to keep in mind. I don't want to write two different sets of wave functions all the time. So just notation. Now let's look at the wave function of the boson. For our system, we have psi n x1, psi m x2 plus psi n x2 psi m x1, 1 over square root of 2, if n and m are different. That's the wave functions are different, and it is equal to psi n x1 psi n x2 if n is equal to m. Now, if they were fermions, we would have this minus sign over here. So I can still use the same single particle wave functions even if it was a fermion. The single state wave function can be symmetric or anti-symmetric, but the two particle state should have this minus sign in between because the total wave function should be anti-symmetric under the exchange of the coordinates. But now we are dealing with bosons.
Then, for fermions, you would have
Of course, because they have to be in different eigenstates. In a given state, you can have at most one fermion. That's Pauli exclusion principle. You have heard of that? The Pauli exclusion principle? Okay. Now I'm asking because, it might be, you took 431 in different classes, and I'm not so sure what you are covering in each one of them. So if there's anything that doesn't sound familiar, even if it's just you, I don't mind repeating them. Probably the other ones will also benefit. So you have forgotten after 1 year. Okay, now we have the unperturbed wave functions. Now we can look at the solutions, the perturbation. Now we have the perturbation. Perturbation corrections. So now the first order correction, first of all, is this a degenerate system or not? Do we have degeneracy in this system?
There are two particles, right?
Yes. What is the degeneracy? So let's write the energy values. It is h bar squared k1 squared divided by 2m plus h bar squared k2 squared divided by 2m.
The only K2 exchange it with one degeneracy square.
Is there a degeneracy if we exchange k1 and k2?
seems
It's the same state. It's not a different state. So there's no such degeneracy. There's only a single state in which the one has momentum k1, the other one has momentum k2. Now, let's see. This is h bar squared over 2m, and we had 2 pi over L n plus, let's say, 1 over 2 squared plus m plus 1 over 2 squared. And
But still, like 5, for example, then 170 still some way, right?
well, let's see, 5 is, well, you see, the problem is it possible to have 4 different integers such that a squared plus b squared is equal to c squared plus d squared? So if there are integers or half integers or that satisfy this equation, in that case there is a degeneracy. But I mean, for the ground state, there is no degeneracy. For the first excited state, then there is no degeneracy. Second excited state will be 1, 1 or 0, 2. Well, let's see. Now, let's write the one particle energies, eigenvalues. Remember, we have the energy h bar squared over 2m n plus 1 over 2 squared. Now, the reason why I put that 1 over 2 in parentheses is that we have, for the ground state, we don't have that 1 over 2. No, for the ground state, we have that 1 over 2. For the first excited state, we don't have that 1 over 2. Because the states go as symmetric, antisymmetric, symmetric, antisymmetric, etc. This is my ground state. This is my first excited state. This is my second excited state, etc. So the ground state is h bar squared over, well, let me forget about this one. So this is 1 over 4, the ground state. The first excited state will be with that, without that 1 over 2, but n is equal to 1. That is 1. Then we will have 3 halves squared, that is 9 over 4. 4, 3, 7, 49 over 4. Etc. So these are the one particle energies.
What if we don't see up to now?
I mean, okay, you see, let's imagine if you are not in a classroom but in a real life situation. You will know which states you are interested in. And for that state, you can check whether it has a degeneracy or not. So let's look at the two particle energies. Just a couple of them. Of course, it will be in units of h bar squared over 2m. Well, the two particles can be in the 1,4 energy state, so it will be 1 over 2 or 5 over 4. Then I have, this is ground state, first excited state. So then we have the ground state, second excited state, or first excited. The first excited is earlier, 2, 9 over 4, etc.
Next state up to on the left hand side for single part. After 4, it is 25 over 4.
Well, 4 is 2. Yeah, you're right. 25 over 4. True. Well, at least the first 4 levels of our state are not degenerate. This is the ground state. First excited, second excited, third excited, etc.
How do you get 9/4?
9/4 is, oh no, I can't get 9/4. It is 10/4. Or 5/2. And okay, that's also degenerate. Non-degenerate. There's no degeneracy at least up to this level. So we don't need to worry about degeneracy. We can just calculate the correction. Now we said it is lambda times Dirac delta x1 or minus x2. Let's stick with the ground state as an example.
I don't understand why we just put first states first. 3 exact states. That in the higher exact states there may be.
Sure, I don't know. Does this equation have integer solutions or half integer solutions? If it does, then we have degeneracy. If it does not, we don't have degeneracy. I don't know. But at least for the first 4 states, there is no degeneracy. Maybe in the highers, of course, there is degeneracy. But if you are looking at the correction to the ground state, we only need to worry about the states that are degenerate with the ground state. Or if you are looking at the correction to the first excited state, again, we need to worry only with the states that are degenerate with the first excited state. We don't need to worry if there is, the degeneracy in the fourth excited state until we try to calculate the corrections to the fourth state. Let's stick with the simplest one, the ground state, for both of them. So psi will be 2/L cosine pi L/2 x1 cosine pi L/2 x2, no, pi over 2L. No, pi over L. When I said x1 or x2 is equal to L/2 or minus L/2, it will be cosine pi over 2, which is 0. So this satisfies the boundary conditions, and this is my ground state. The first correction to the ground state will be psi, this is psi 0, v psi 0. So how do you calculate this? This is d cubed x1, d cubed x2, psi 0, x1, x2, v psi 0, x1, x2. Well, we have real wave functions. And since v is Dirac delta, this is lambda. Are you familiar with Dirac delta? Okay, this is lambda times d cubed x1 psi 0 star x1 x1 squared. And this is equal to lambda times, no, not d cubed. We are in one dimension. This lambda times 4 over L squared dx1 from minus L/2 to L/2 cosine pi over L x1 raised to the power 4. Okay, whatever that is, you can just try to evaluate. I will not. Well, E0, which is, by the way, less than 4 lambda over L.
That's not correct.
No.
Yes.
Hmm? Cosine, I mean, you can just look at the dimensions. Cosine is always less than 1. So if I replace the cosine by 1, then I get an upper bound. If I replace cosine by a 1, the integral just gives me L, so I have 4 lambda over L. Now E0, if you remember, that was h bar squared over 2m and 1 over 2. Now 2 over L times 1 over 2. Right? So the symmetric one, the cosine, yes, 2 over, no, it's 1 over L pi. Yeah, pi. Of course, I have 2 of them. Both of them have the same energy. So these 2's cancel, and I end up having 2's cancel. Here I have a squared, h bar squared, pi squared over m L squared. Now there was this question whether this series converge fast or not. So we have to look at the ratio of the correction to the unperturbed one. So if you just take the ratio, this is, let's say, less than 4 lambda over L times m L squared over h bar squared pi squared. Now the L's cancel. This is 4ml lambda divided by h bar squared pi squared. So if this number is very small, then probably first correction would be enough. If this number is large, then we have to go and calculate the other corrections.
It's 10 to the 4 plus 4 in the denominator.
Hmm?
There is 10 to the third minus 34 square in the denominator.
Well, you see, let's see, what part, I mean, that is one mistake that you shouldn't do. What is M? Is it electron? What? But is it an electron or, I don't know, lighter particle? This is a boson, so it cannot be an electron, but maybe the hydrogen atom. We don't know. So, I mean, all these things are dimension full quantities. So I mean, you cannot say that a dimension full quantity is large or small. It depends on, I mean, the numerical value depends on which units you are using. For example, if you ask me what is the value of h bar, I would say it's 1. In the units that I use, it's just 1. So that's not small. So I forget about h bar.
So what's the solution?
No, there is no solution. I mean, you have to actually pick up a physical system. And look at whether what is lambda. You have to identify some lambda. And you will, of course, if you have a physical system, then you know what M is. Now, we will have this case when you look at the hydrogen atom. That's a physical system. How do you feel? Do you want a 5-minute break? Okay, let's give a short 5-minute break and then we can continue.